Hey guys, welcome to the very last of your thermodynamics videos and the very last of delta G. So let's get right into this and keep it nice and short. So we have already talked about three ways to solve for delta G. So there's the molar free energy, there's this delta G equals delta H minus T delta S equation, which this one will come up again later on in this video, and then Hess's law. So all that is left is to talk about it in terms of equilibrium. So that is this equation, delta G standard equals minus RT ln K, or as we affectionately call it, RatLink. So delta G equals RatLink. So quick equilibrium review, since this way looks at solving involving equilibrium problems. So reactant 1 plus reactant 2 equals product 1 plus product 2. So the rates for both sides, well, the forward rate is going to be this rate constant times reactant 1 times reactant 2. Rate in the reverse direction is a different K times the product concentrations. So we can put the two rates equal to each other. So forward rate equals reverse rate. And that gives us this equilibrium expression. So big K equals the rate constant forward over the rate constant in reverse, or products over reactants. So equilibrium expression review. So if we have this reaction right here, nitrogen gas reacting with oxygen gas to make nitrogen oxide or nitrogen monoxide gas. So we would get this equilibrium is equal to this product squared, because of this 2 factor right here, over the concentration of the reactants times each other. We can look at it graphically too. So we have A, B, and C. So reactant A is producing B and C. And you can see from this production line. And right here, this highlighted area is where the system reaches equilibrium. So products over reactants, so concentration of B over concentration of C, or concentration of B times concentration of C over A squared. And if we read the graph values, we get this right here, so we can solve for K. So going back to what K means, again, if K is larger than 1, then that means products are favored, so we'll have more products produced at equilibrium than we will have reactants. If K is less than 1, we should have more reactants overall than we have products. And so that is everything that you need to get us started here. So that's going to be the K right here in this RatLink equation. So RatLink, again, is delta G is equal to negative RT ln K, so this is that equilibrium constant. If the system is at equilibrium, then delta G should equal 0. And that means that R equals, this is the R value that we'll be using, so 8.3145 joules per mole degree Kelvin. If we turn this in kilojoules, we just move that decimal over 3 spaces, so 0.008. So this is not the same as the gas law R, so make sure you remember which R you're using. It should have the joules value in it. And then K, again, is the equilibrium under standard conditions. Of course, here it also has to be raised to the power of their coefficients, so based off of the stoich. Right here is a good Bozeman science video on this whole thing if you want to watch that. So there's the link for you. Okay, so moving forward from here, just kind of a comparison thing. So if delta G standard is negative, then that means that products are favored, K is going to be greater than 1. If delta G standard is 0, K equals 1. And then if this is a positive value, then K is going to be less than 1. So what is delta G equal to 0? So this is, again, not the standard delta G. So it means equilibrium. There is no net movement in the reaction in the forward or reverse direction. So complete equilibrium. So reverse and forward rates equal each other. All right, so here's the first example of this RatLink thing. So calculate delta G at 298 degrees Kelvin, so this is standard, and then we have these pressure values. So we're assuming this is equilibrium because it's an equilibrium problem. So we can set up that equilibrium expression, plug in the pressures. So this is Kp right here, and we get this. And remember that K doesn't have any units to it. So we get this value for K. So we can look at the delta G equals RatLink thing. So again, negative, this is that R value in kilojoules. The temperature is right there, and then natural log of what we found for K. So that gives us delta G at 11.59 or 11.6 kilojoules per mole. Again, if you use the R value here, if you were to use the joules version, this would be joules per mole, and it would be quite a bit higher. So pay attention to which R value you're using, because it will affect this unit right here. Okay, this particular problem is quite a bit harder. So it gives us the resting of iron. It gives us these standard values, so standard delta H standard and S standard. So I would ask that you guys probably pause this video and just look at this problem and see if you can't figure out how to set it up, and then on the next slide I'll show you how to solve it. So I would recommend pausing it and looking at it, but moving forward, here's what we get. So we use that delta H value, products minus reactants. Well, we only have one value because the others are elemental form. So we get this for delta H. We can do products minus reactants for delta S, and that gives us this value in joules or kilojoules. We want to use the kilojoules. Here's that delta G equals delta H minus T delta S. So we can plug those values in, and we get this delta G value, which means that delta G, put that equal to the RatLink equation. We can rearrange it to solve for K, and we get this. K equals e to the 601.4. Now, if you notice, if you try to plug this into a calculator, you get some error code because your calculator can't deal with this number. So we'll just leave it at that and report it as that. Okay, so this is just a quick breakdown, and then we are done. So if we have a system that is not at equilibrium, so again, here is that delta G value, here's delta G standard plus RTLNQ. If the system's at equilibrium, this value is 0, so we can move this over, and this would be a K value, which is where the normal delta G standard equals negative RT LNK comes from. But since we're not at equilibrium, this right here and this right here have to add up to what the normal delta G. So free energy under the given conditions. This is under standard conditions, which is that 25 degrees Celsius. So 298 K. And then here Q is the reaction quotient used at given conditions. So normally K equals products of reactants, but we're not dealing with K. We have Q instead. So Q equals products of reactants, and then this gives us a solve for the equilibrium condition. So we would need to know what it is at standard, and then we would need to know this stuff, and we can get delta G at that point, at that Q point. Beyond that, that covers everything you need to know about delta G, so you should be able to rock out those practice problems from now on. And let us know if you have any questions.